As you know that there are the detection systems like in case of the protein estimations or the kinetic studies, you people perform the ELISAs. Like in ELISA, it is an endpoint detection. You are attaching a kind of a tag to that. But there are the other UV spectrophotometer based, like where exactly you are measuring at a 280 nanometer due to the tryptophan excitation, aromatic excitations, or sometimes you are attaching a fluorescent tags. Those are called as a labeled based. Even in case of your iTrack or the iCat based in mass spectrometry, you are attaching a tag right there. Here, label free detections, where exactly label free detections comes is, there is a different concept, solution interface, solution solid interface. These are the two techniques. You heard about ITC techniques, isothermal calorimetry based titrations. It's where exactly if there is a two proteins are interacting together, what is the energy is absorbed or released into the reaction system. This is we call it as a solution interface. I think in the last this one there is a one technology called as a nanotemper. It is a kind of a once again solution based solution interfaces. Here I am going to discuss about the solution solid interface. What exactly the solution solid interface? So one of the protein, say suppose two proteins are interacting together, one protein we have to be put it on a solid support and another should be in the solution form. That is what we call it as a solution solid interface. Okay. I am going to discuss about this, what exactly this BLI technology is. BLI is nothing but the biolayer interferometry. SPR technology, it is a surface plasmon resonance. Here we have like a BLI technology. The technologies are different, the output from the SPR or from the BLI is the same. Okay. So how exactly this technology works? The word interferometry, once again light is coming to pictures, the optics. So as you know that light, it consists of a waves once again. When it propagates in the same direction, we call it as a constructive interference. When it is in a out of phase at 180 degree, we call it as a destructive interference. So constructive as well as the destructive interference makes the signal pattern here. How exactly? So we are using a sensor based device here. If you look at this is the sensor, this is made up of the plastic, this is the glass, consists of a fiber optic inside. So if you look at this diagram, at the tip of this we have some kind of a coating, we call it as a biocompatible matrix. To that we are going to attach a protein of your interest, we call it as a ligand. That is what we are going to immobilize. This is what we call it as solid support. So in case of ELISA, you are also coating one of the protein onto the plate, right? Similarly, we are coating onto the sensor. If you look at next diagram, look at the diameter of this. If it is just only a 600 micrometer, it is a two-dimensional binding surface, the when we protein immobilize onto a solid support, and the biocompatible matrix is something like it is inert in nature. You can use any kind of your buffer systems, pH from 1.5 to pH 9, we can easily work. Most of these biomolecular interactions we are working at the physiological pH. So how exactly this technology works? As I told, it works on the interference pattern. Interference patterns make the signals here. I am passing a light, it is a white light, it is just only from a 400 to 800 nanometer, it is not a UV based. So I am passing the light get reflected back, it is a reflection based phenomenon. So one of the light which is coming from the internal optical layer. So suppose when we say that there is an interference comes, so suppose I am putting one stone into a water, you see that there is a waves, right? If I put two stones simultaneously to a water, what happens? Waves will be going that side, but this side there is a, like each are mixing together. Then they call it as an interference. Here, due to this biocompatible matrix, always there is a kind of the block, some light get reflected back. It is not like that only a 5% of the light only get reflected, rest of the 95% will be transmitted in the well. So one light which is going through the ligand, due to your ligands there is a kind of obstacle here, once again light get reflected back. Constructive interference makes the signal rise, destructive interference makes the signal drop. So suppose when I same sensor, when I dip into the corresponding binding partner, I am giving an example. Here I am quoting a sensor with a protein A matrix. Protein A have a strong interaction with a monoclonal antibody. Okay. So, if you look at this diagram, the antibody starts binding to this ligand. Now, earlier there is a internal, always there is a constant from the internal optical layer. Now, there is a reflection coming from the here. If you look at this, there is a path length get increases. Earlier was coming from the light was coming from here. Now, the light is reflecting from the here. So, this optical path we are measuring in terms of the optical thickness. That optical thickness we are measuring in terms of nanometer binding. See, more the molecule starts binding onto a sensor, there is a more shift in the spectrum. As the molecule starts binding, earlier you can able to see, if I go back, this is the your wave. Okay. Due to the binding, we can able to see there is a shift in the spectrum. We are going to measure the shift as well as the optical. The response, the intensity is the function of the shift in the spectrum as well as the optical thickness. This is what the principle behind here. I am passing a white light, okay. Light get reflected back. One I said from the internal optical layer due to the matrix, another from the ligand end. So, you can see that all these ways, constructive as well as the destructive interference. Constructive interference makes the signal rise, destructive interference makes the signal drop. The same sensor, when you dip into the, say suppose I gave an example last time like that, protein A immobilized onto the sensor, then I am dipping into the corresponding analyte as an antibody, as an analyte. So, suppose I am dipping the sensor is already coated with the protein A. Now, I dipped into the corresponding antibody solution. Now, you can see there is an orange thickened layer, right. This is due to the interaction between the protein A and the antibody. Now, you can see light get reflected back from here, earlier was from here, now from here. Due to this, you can able to see there is a shift in the spectrum, the path length get increases, right. That is, that path length is also dependent on the concentration. More the concentration, more the molecule starts, your optical thickness get increases. If it is a less molecule, then the shift will be less. Due to the interaction, we can see this, there is a shift in the waves. Can you able to see these patterns? This is due to the interactions. Now, as the molecule starts binds, the real time you can see there is a, as the molecule starts pressing, there is a curve like this. This is what we are, the readout is. This is what the background, this is what the readout. Okay. See, this is what we call it as the association phase. As the molecule starts binding to the binding partner for that, we can see there is a curve rises. This is, we call it as association. Once if we like same sensor we bring back to the buffer, then the bound molecule to the receptor get washed off. Okay. Now, we can see this phase we call it as a dissociation phase. So, dissociation by the association we call it as a affinity. So, say when we say kinetics, see most of the people do the label based platforms, kinetic studies like ITC the people do, the people do the ELISA based methods, but all the other methods only give a affinity constant. Say suppose I can plot like a sigma like this at the midpoint in the IC50, what we call it as affinity. There are the equation to calculate the affinity, but label free platforms are the only instruments which gives the on rate and the off rate value. None of the any other instruments gives the on rate and the off rate. What is on rate? On rate is nothing but the association rate. Off rate is nothing but the dissociation rate. So, dissociation rate by the association rate gives the affinity. So, we have to determine these affinity constants. These affinity constants, if say protein are interacting strongly, this affinity we are in terms of called as a picomolar affinity. If there is a moderate interaction, say suppose when antigen binds to an antibody or a protein binds to a receptor, you will see the association phase. Now, it starts dropping when in the dissociation phase. This, if it is like this, we call it as a moderate interaction. If it is like a strong interaction, like straight line from here, this is we call it as a picomolar affinity. What exactly is picomolar affinity, nanomolar affinity or micromolar affinity? Say suppose in case of the drug discovery or anything, you require a small amount of a drug to elicit a response. Just a like a picogram material or a autogram level, that much concentration is required to elicit a response or efficacy of the drug even, I mean to say. So such kind of things comes into picture here. Less concentration, more response, longer time in the body. That is we call it as a strong affinity towards the receptor. If say suppose giving an example, doctor says that you have to take a paracetamol 3 times a day. It indicates what? Means drug is not much have a like affinity towards the receptor. Otherwise some tablets people say that you have to take it a 1 tablet per. Even some injections are there once in a month. These are what? These are the how strong, how weak are these are binding. Based on that we can decide the dose. Okay. So I will go through this. We have a Paul Corporation. We have a like a different platforms for the designing the experiments and the perform the in the discovery. From some single channel, it is a very small. In one hand you can hold. Looks like our nano drop machine. Single channel, manually operated, one sample at a time. Okay. This is 8 channel instruments. What I brought this one here. At a time you can go for 8 sample. You can finish off the kinetics or the quantitation studies. Say suppose quantitation in you are something like expressing a proteins which have a question. So on basis of these are the instruments like this is the 8 channel, 8 sample we can measure at a time. We can perform like different dilutions in the kinetics, higher to lower dilutions we can perform, and we can conduct a kinetic studies here. And this is the see here for the red instruments we can see the dynamic range wise. The maximum we can go from 10 picomolar to 1 millimolar, that is the dynamic range we can go. And the size wise interactions, say suppose small molecule protein interaction, protein interaction, vaccines, virus, live virus, bacteria and all, we can able to perform. Here with respect to the size wise, 150 Dalton is the minimum detection to the mega Dalton protein interactions. Mega Dalton in terms of virus like particles, it is like a very multimer, it is we are measuring in terms of the nanometer, not with respect to KD or size wise, it is such a big. We can able to do still quantitation. In case of vaccine industry, people are using this machine for the quantitation purpose. And this is the one, this is the blue model, it have a similar 8 channel function, but this instrument not able to useful for the small molecule interactions, small molecule protein interactions. Only we can go protein to megadaltons, less than small peptides or small molecules not possible with this. This is the one recently launched. This is a 2 channel, especially for the academia instruments. It only takes 2 samples in one at a time. These are the very high throughput instruments. This one 384 well plate formats, 16 channel instrument. The sensitivity is similar to this red one, and we can perform like a quantitation and kinetics at the high throughput level. The blue one once again sensitivity is similar to the only for the proteins, not for the small molecules and the peptides. This is the high throughput machine. This is also very recently launched. It have a 96 channels. So suppose if I put a 96 well plate, in one stretch 96 sensor it will pick up and go to the 96 well plate. You can read a quantitation in 2 minutes. So such a high throughput level. So this is what the readout is, how it comes, the example I had shown. Kinetics actually, how we are performing this kinetics. Giving an example here, one of the sensor, it is a streptavidin coated sensor. The matrix is streptavidin here. I am immobilizing an antibody which is biotinylated, and then this is, if you look at, there is a response like this. The sensor just it is a baseline. When I dip the sensor into the corresponding biotinylated antibody, you see the gradual rise in that. The same sensor when I bring back to the buffer, unbound material get washed off here, and the sensor now I dip into the corresponding association, see the antigen, we see the curves like this, different dilutions, 2-fold or 3-fold, however you are making. This is what interaction between this antibody and the antigen. Once again the sensor I bring back to the buffer, we see the dissociation. So this is what completely we call it as a kinetics. Yeah. So advantage is like that on the biolayer interferometry, it works on the dip and read format. So just in the 96 well plate, we have put a antigen, antibody and all that. The sensor, it will move like this and we can read. And advantage is like that there is a no microfluidic devices. In case of the SPR, it works on the principle of the microfluidics. You know, in HPLC there is a pumps, peristaltics pumps, it will deliver the mobile phases. In case of the SPR also, there are the buffer systems, it will deliver the mobile phase or the buffers on the sensor surface. So what happens is this in the microfluidic devices, we can't use a kind of a samples like crude samples. Suppose from the serum, if you want to do a serum analysis, serum sample analysis, or the body fluids, or the samples from the bioreactor itself, because it contains so many other kind of contaminants and all, it blocks the flow cell. Once if it is blocks the flow cell, we have to replace the complete assembly. That is what the expensive in case of the SPR, microfluidic devices. But here it is a depend rate. Something goes wrong also, we can throw a sensor, but there is no any other kind of such fluidic devices here. And the high throughput, I said it is like a 8 channel, 16 channel, depending upon the application we can use. Unparalleled and easy of use. I can show you how the software is so user friendly. Just if I train a half an hour for you, you yourself can work on this instrument. Such a user friendly, anybody can be operated. In case of the SPR, you require a dedicated operator for that. So here that is such a easy system. Versatility, sample I said you can take from the crude or the purified or the unpurified, any kind of samples we can go, and the pH, you can work from the pH 1.5 to pH 9 depending upon your applications. Most of these biomolecular interactions we are working with the physiological pH. The price wise, if I compare the sensors, SPR sense chips versus this biosensors, this one sensor costs you something like a $5, and you can regenerate this sensor. Okay, just perform the instructions, I can regenerate the surface, I can use next time. At least these sensors we can use for the 10 times. Okay, that is what the advantage is like that. In case of the SPR also, people are regenerating. If it is something goes wrong in case of the SPR chips, you have to throw the complete sensor. That sensor cost you something like $150 to $200 depending upon the what chemistry you are buying. Here this is like 96 sensors we are providing, 96 different kind of experiments you can perform here. That is the advantage. So I will skip. If you look at the inside of the instrument, this is, we call it as a sensor rack. This is the optic box, consists of a spectrophotometer inside. It is an 8 channel instrument. Each channel have a 1 spectrophotometer built inside, and this is your 96 well plate sample compartment. It will move in this fashion, parallel. Okay, it have like a temperature controller as well as the orbital shaker. So here I said we don't have microfluidic devices. To assist a binding, we require a shaker. So shaker enhance the binding. So this shaker we can work from 100 RPM to 1500 RPM depending upon the application. Say suppose when I can use what kind of RPM. So suppose if I am working with a very high concentration, I can reduce the low RPM, 400 or 500 I can work it. If you are working with a very low concentration, then I have to increase the RPM speed. So shaker will enhance the binding. This is the 8 channel. We have a 384 model. This is what the optical head is. This is the HTX, I said high throughput instrument, multiplexing. Here the advantage for this instrument in the HTX is we can analyze one sample also, we can analyze 96 sample also. It is a multiplexing. If I have like a 16 sample, I can choose 16 heads. If I have like a 48 samples, you can choose 48 heads depending upon. The last single, the Blitz instrument, it is a single channel manually operated. You have to put the sensors manually and then read. But rest of these high throughput instruments are all automated. So as I mentioned the biosensors, we have around 16 different chemistries with us, and depending upon your application we can choose. Like streptavidin and the amine coupling, amine reactive, these are the useful for the custom protein quantitation as well as the kinetic studies. So streptavidin, here one of the protein you have to do a biotinylation, then you have to immobilize. In case of the amine reactive, there is a kind of chemistry we have to use, like it is your N terminal or the lysine get involved covalently coupling to the sensor surface. So we can work the versatility of the interaction except cells and the atoms. In the blue whatever is there, all things are possible here. Cells is something like in terms of the micron size. If you look at the surface of the sensor, it is just hardly can hold like a 3 or 4 cells on that. It's very difficult to work on the cells. Rest you can even have like publications on the bacteria, entire bacteria, virus and all. 0.2 micron, such kind of applications we can work. How exactly it works? For a quantitation purpose, 8 sensors, I am dipping here. You can see generate a different concentrations here from say from 100 microgram per ml, 2-fold dilution. If I go 8 concentrations we can determine, 8 samples read at a time. Think about if you are performing even a UV based one sample, how much time it will take for a reading. So roughly 8 concentration or a 6 data points, half an hour time. Each time you have to wash the cuvette and then put a next concentration. But here the advantage is like that, here it's purely an affinity based, you will get. In case of the UV, I am giving example, you people are performing the Bradford assess, right? It's what you are doing is it is a purely and total protein quantitation, not exactly the protein of your interest. Even in case of the HPLC also, it is at a 280 monitoring, it is a once again resolving, but even though you do not know how much pure is your peak, there may be some other proteins which have a same hydrophobicity, it will elute at the same time. That is also something like that. Here we can purely an affinity based interaction. If you have a specific antibody or a specific receptor, then we can easily quantitate the how much protein is in your the expression. Now if I dip into the unknown sample, you will see these are the unknown. From this data points we can easily calculate the how much protein is there. Very simple. We can do a different kind of experimental designs here. Whatever I had shown is called as a direct binding, 1:1. This is your antibody or antigen or a protein. Here we can go work from low mg per ml to low nanogram per ml. The instrument dynamic range is 50 nanogram per ml to 2 mg per ml. This is what we call as a direct binding. So suppose your protein expression is in the nanogram or a picogram level. That time we require a kind of a secondary antibody to amplify the signal. In case of your ELISA, you people use as a secondary antibody, right? Similarly, we can use here secondary antibody to amplify the signal. Here the concentration we can go from low nanogram per ml to low picogram per ml. So suppose I want to replace the complete ELISA onto this instrument, yes, possible. That is also there. As if you look at the optical thickness, right? As in the principle I said, more the optical thickness, better the amplification. If you see, so many things are here, we can amplify the signal. How exactly kinetics works? Just I will put a sensor, take a buffer, dip into the buffer, I will get a baseline. I am just as a PBS buffer. I dip into the bioattenuated antigen. You can see there is this step we call it as a loading or the immobilization step. Okay. Then I will dip the sensor back to a buffer, unbound material gets washed off here, dip into the corresponding binding partner, the antibody, we see the association. When the sensor will bring back to a buffer, we call it as dissociation. So in one stretch we can do the 8 samples at a time, 8 different concentrations. Okay. These are some of the applications. We have around more than 1000 right now. This technology started in the year of 2004. FortiBio launched this instrument, and later it's picking up, and people have so many in case of the academia, they had come up with this kind of publications like DNA aptamer screenings, antibody, liposome antibody, like say GPCR. So such kind of things we can immobilize onto a sensor surface and work. Kinase interactions, yes, we have a data on this. So around more than 1000 we have right now. Application wise, this is the compare with this guy is David Miska from University of Uppsala. He is a pioneer in this area, biomolecular interaction. He has compared the interaction of 50 kilodalton Fab binding to a 60 kilodalton antigen with respect to different SPR models, and with respect to FortiBio, it is almost all the data are same. Because SPR technology is a very old, almost like a 30 years it is in the market. Now we are the FortiBio almost like a 10 years in the market. This is the example I am showing a comparison with the SPR. This is a small molecule. These are the carbonic anhydrase inhibitors. So carbonic anhydrase was immobilized onto a sensor, and then these are the drugs inhibitors passed on this. These are on par with the results. This is also once again the publications by the MISCA. This is one of the example protein A quantitation, histag protein A. It is the dynamic range is 250 nanogram per ml to 16 microgram per ml. So here they had performed the media versus just only a buffer. It is on par. The results are. So we can use even for the to quantify the protein in your culture. This is one of the examples. These are published examples. Anti-influenza antibodies using for the histagged antigen kinetics measurement. This is the isotyping example, serum using isotyping of the anti-influenza antibodies in the serum using histagged antigen captured on octet rate. See, if you look at this, there is only one which is have a affinity towards that we can able to. Rest is the baseline. This is the lipid vesicles with respect to peptide. These are the once again small molecule protein interactions. This is a DNA protein interaction studies. So suppose this is one of the example, the biotinylated DNA they immobilized onto the streptavidin sensor, then they the apo-YTGR protein they in presence of the ferrous sulfate, you can able to see there is only a binding. They had used a different metal ions here. None of the metal ions use just a baseline. In presence of the ferrous, you can able to see this binding. That's what it is, a very specific interaction. Biotinylated. One of the strand you have to do a biotinylation. Protein biotinylation is easy compared to the DNA biotinylation. You have to do using a PCR, you have to synthesize that. So detection of anti-drug antibody in the serum. This is one of the important for the therapeutic industries, because most of these drugs when we are injecting into the body, body itself recognizes that as a foreign particle, right? Then once again your immune system get activated, it develops the antibody. So we have to detect that. That's we call it as immunogenicity testing. It is important for the biotherapeutic industry, especially those who do. We have to detect that how much anti-drug is there. Is there any this anti-drug antibody is a neutralizing your drug of interest. So nanoparticles, recently this is EGFR targeting nanoparticle present for the thermoresponsive polymer. This is the one of the drug they had make a nanoparticle, then they targeted for the EGFR. And liposome we have. We can use multiple applications. These are just I am going conformational measurement here, folding, unfoldings and all. This is what right now this kind of application in IIT Delhi, Dr. Professor Tapan Chaudhary is working on this area. So in India we have everywhere industry as well as the academia, the installations. Here we have in Indian Institute of Technology Delhi instrument, this instrument is there, sorry. And Indian Institute of Science IISc we have instrument. We have in ISER Mohali the small blitz instrument. Madras University we have a very small single channel instrument. In CBS we have a small single channel. CCMB we have this same instrument in Hyderabad. Rest other in industries people are using for the